Good afternoon, everyone. It seems I'm the last scene between you and dinner, so let's try and get this over with. And without further ado, I'll be talking about the particular complications in properly handling backscatter from multi-sector, multi-swath systems. It's a work between myself and Johnny. So as you all know, about the backscatter strength, it's angular dependence. It's a powerful discriminator of different C4 types. And while it might be very easy, let's call it like that, to distinguish between rough rock and very fine silt, for example, the same is not true for medium sand and very fine sand, as they are, for example, just should be apart. It means that our backscatter strength estimates must at least be definite. However, even if we use the same system to survey the same area, even if the two systems are identical and operating at identical frequencies, they will often return different results. And assuming we are addressing water column propagation and water interaction effects properly, this patchwork built aspect leads us to think that we don't know our system as well as we think we do. Probably its source level and receiver sensitivity, angular dependence, we don't know those as well as we should. And so we need to calibrate our systems. So Rita, I think, has gone through this already, but one way of calibrating the system is using the reference area with isotropic and homogeneous backscatter. For instance, we can use a pre-calibrated sonar, such as a split beam echo sounder, to get a reference angle response curve, or ARC, and then we just compare it with an uncalibrated ARC that we get from our uncalibrated system. Then we compare these two ARCs, and we somehow are able to calibrate our initially uncalibrated multi-beam. And in fact, this principle has been applied. In fact, the kickoff for this project of mine and John was this paper from the Ifremer folks in 2018, where they applied this principle to a 2040 operating with a single sector. However, it seemed to us that they were assuming that the beam pattern was fixed in a vertical reference frame, so changes in the sonar reference frame were not being accounted for. And as I said, they were operating in single frequency, so multiple transmit sectors were not being addressed. So there was some room to work on top of this paper. And to calibrate a multi-beam system, regardless of it being a single sector or multi-sector, we have to consider every of its depth modes. And by depth modes, I mean a combination of operational settings such as frequency and pulse rate, as all of them will have will present different beam patterns. Another thing we have to consider is that our transmit pattern will be sampled at different sonar reference across track angles. Multi-sector systems will also, to achieve yaw stabilization, will also steer each of their transmit sectors in the fore-aft direction, meaning that our received patterns will also be sampled at a wide range of sonar reference along track angles. While we must understand that single sector systems will also steer their transmissions to achieve pitch stabilization, but the steering angles involved are much smaller. And returning to what I was saying about depth modes, in here just popping up this GIF animation to show you all the beam pattern changes for the same system, in this case at 2040, and we are just cycling between modes. So lots of agencies nowadays use multi-sector, multi-swath systems. And so if we manage to calibrate these systems, we will be ultimately contributing to their seafloor characterization methods. And remember, these agencies usually undertake national scale programs that involve multiple platforms, that they survey huge areas under the scope of projects that are meant to last decades. So this is a meaningful research lab. And that brings us to a calibration pipeline that myself and John developed and that I defended in my thesis defense last month. And while I won't go through everything, through every step due to time constraints, I highlight the most important parts. So first of all, we need a reference data set, and thankfully Mike already partially described Ivan Guimarães' work. So what he did was he established several reference areas in British Columbia, Canada. And in here, I'm plotting the data from one of those reference areas. So these are all backscatter, calibrated backscatter observations plotted by grazing angle and frequency. And when you look at this plot, you can already see that the data is noisy, especially noisy at low grazing angles and near normal incidence geometries. But what I intend to do is I will slice this multispectral ARC at a specific frequency. And in this case, I'm selecting 80 kilohertz because it's the center frequency of the center sector of the first swath of an EM710 operating in very shallow mode. And then I try to associate to it an ARC, a reference ARC. And to do that, I apply a GSAB model in that data. And I can do that to all the other frequencies that this system in this mode uses. And now I have a reference ARC for each sector. The next step is dealing with the applied gains applied by the manufacturer. And continuing with the EM710 example, the manufacturer in this case would be Kongsberg Maritime. And I would like to have my data uncalibrated or calibrated, but without any gains applied by the manufacturer. But what Kongsberg do is they apply a TVG, a time varying gain, to suppress the specular peak of the backscatter data and to flatten the angular roll-off. And I think they do this so that the user in real time can better distinguish between seafloors with different acoustic properties. And so if I want to remove this TVG, I have to be able to reconstruct it. And Kongsberg's TVG has three components: a immersion component, a near normal incidence correction component, and an insonified area component. The first two I mentioned, they are well documented. We have all the necessary parameters we need they are recorded on datagrams, and so we can recreate them and remove them. In what concerns the insonified area, that's not quite true. In my opinion, at least, the documentation is insufficient. We don't really know, for example, what pulse length is being used in their assumptions, and if, for example, the beam widths they are considering are corrected for steering or for frequency. Thankfully, the PMO, the not so new anymore, Kongsberg new format fixes this because the TVG that is applied onto the data is actually stored in the datagrams. And so these ambiguities don't exist anymore, and we know what has been applied to our data. What I do next is I take every estimate that I can get from our multi-beam that we want to calibrate, and I map it in a sonar referenced space. And to do that, I apply the geometry that Anandi Roji developed during his PhD. It has more to it than I'm about to say, but it's basically, I compute the sonar referenced across track angle and the sonar referenced the long track angle. It's not quite this, but it's enough for the scope of this discussion. And finally, I try to actually derive the string of SP of backscatter strength correctors. And to do that, I subdivide my data set into sectors. And now let's look at a specific sector. And I subdivide the data that falls under a specific sector in sonar referenced angle beams. And let's look at the data that's in one of these specific beams. We can further group it in several grazing angles, and that happens. We'll have several grazing angles because for the combination of sonar referenced angles, we'll have different seafloor morphologies, or our vessel will present, we'll have different attitudes. So we'll have many boats or many slopes. And to deal with this, I just select the grazing angle sub-beam with most samples on it. So looking at this grazing angle sub-beam, not sure you can see, but we now have on this histogram two vertical lines. The red dashed line is our average and calibrated backscatter from all this data. And the other one, which is the dash dotted purple line, is the reference backscatter associated to it. And remember, how do I get this reference backscatter? Well, I have defined the reference ARC for each sector, and I know with which grazing angle I'm working with. So extracting reference backscatter becomes trivial. And my corrector for this particular case is just the difference between the two. It's that simple. So I can repeat this for every bean in the sector and for every sector in the data set, and I end up with what I call a correction, a backscatter correction heat map. To help you understand this plot, the top row contains the sectors of the first swath, the bottom row, the sectors of the second swath. The y-axis, it's the sonar reference angles in the along track direction. The x-axis, sonar reference angle in the across track direction. And for us to better understand how these corrections vary, for example, in the across track direction, we can slice it at a specific along track angle. And this is how the corrections vary. And you can already see that, especially for the outer sectors, we have some quite large corrections to perform, more or less 7 dBs in this particular case. Similarly, we can also see on these two plots that just appeared how our corrections vary in the along track direction. So in here I'm presenting the uncalibrated data also from an EM710 before applying the correction heat map. Again, you can see those departures from that black dashed line, which represents the reference ARC for each sector. You can see the same, about 7 dBs of difference for the outer sectors. When we apply the correction heat map, as we expected, the data snaps into the reference that was used. Now we can look at the same data, but now in a more of mosaic format. The uncalibrated data is what is showing up right now. You can see the sector boundaries, and you can also see some strange artifacts over here. But when we apply the same correction heat map I showed you before, these strange artifacts, which were associated to yaw stabilization, disappear, and our sector boundaries also go away. So we went to the calibration pipeline that we developed. However, the question remains, if I use a different reference area with the same system, using the same mode, will I have the same correction heat map? I should, because it shouldn't depend on the reference area which calibration I get. So we tested for that. We took the same EM710, operating in very shallow mode, and we got correction heat maps from one area, which is shown on the left side of the slide, and another area with a different seafloor type and a different depth as well. And we got the correction heat map for it. And now I'm just going to try to flick between the two heat maps, and you can already see that there exists some differences between the two. And in here I have the difference heat map. So I'm subtracting just one heat map from the other. And immediately you can see that our differences for this particular case are within plus or minus 2 dB. You cannot, it's not that obvious, but we have an average bias of about 1 dB, and superimposed on that, we have this range-dependent trend that we attribute to a miscalculation in attenuation. You can probably spot it in the outer sectors. However, at nadir, we have another problem. We have a more strange artifact, about a 1 dB departure from that average bias. We don't really know why that's happening, but we suspect that we are obviously not handling the near normal incidence geometries as perfectly as we should, and we think there is some problem with the insonified area that we are using. Of course, on top of it, our reference data might as well not be good enough, especially at nadir. And when we are using split beam echo sounders, the EK80 family, they don't have such a smaller beam width, and there might be some problem with the resolution of our reference ARC at nadir, especially at nadir. Finally, we tried to do something different. This time we were using an EM712, which we calibrated at one of Ivan's reference areas. This reference area marked here with the red circle. And so we took our now calibrated EM712 and tried to survey this area highlighted by the blue rectangle. We saw from N-calibrated backscatter data that it was homogeneous, and so we surveyed with this now supposedly calibrated EM712. And we did it at two different modes, very shallow and shallow mode. And these were the ARCs that we got from that area. The main difference between very shallow and shallow mode is the pulse length that is being used. The frequencies are not identical, but they are just about 11 kilowatts different. It's the max difference between the two. So we should expect a very similar ARC, regardless of which of these modes we would consider. And as you can see, they agree quite well up to 80 degrees of grazing angle. But again, near normal incidence geometries, we have that strange behavior on our ARC that we again attribute to either a combination of the two. Our reference data set has some problems, or we are not handling the insonified area at these geometries quite well. To conclude, we think we have developed, in general, a viable method to achieve calibration of multi-sector, multi-swath systems. Still, and addressing this community, I think a few issues remain which we will try to tackle together. For instance, is how could we obtain more reliable reference data, and how could we solve this insonified area issue at near normal incidence geometries. And thank you for standing by and for listening to me. I'll be able to discuss this further if you want me to. Thanks.
Miguel, any last questions for Miguel? At the end of the day, I'm sure people are ready for some refreshments. It seems that we start the conversation for tomorrow, unless anyone's got a burning question. Miguel. All right. So I thank everybody for participation today. Big round of applause for all the speakers. Tomorrow morning, we will be starting at 8 o'clock. We've kind of staggered the days, late one day and early the next, just to kind of accommodate people in the different time zones. So we've got some more presentations in the morning.